Welcome to the 1936 Nobel Prize in Physics, which was actually divided amongst two scientists who you've probably never heard of, but I'll bet you've heard of what they discovered. So it was divided between Victor Hess for his discovery of cosmic rays and Carl Anderson for his discovery of the positron. Not the electron, positron. These are two very different yet fundamental discoveries. In fact, cosmic rays help scientists discover all sorts of other things like antimatter and a thing called the muon, which is really sort of a first cousin to an electron, but that's a whole different video. And the positron itself was really kind of our first look at antimatter. So here we're going to have some fun until antimatter comes along and just annihilates the whole thing. See what I did there? All right, so let's take a deeper look at these two gentlemen. Victor Hess's portion of this prize was for cosmic ray work he had done between 1911 and 1913. Now, what are cosmic rays? They're particles or clusters of particles, which are essentially atomic nuclei that move throughout space at nearly the cosmic speed limit or the speed of light. Now, there's always some measure of ionizing radiation that can be detected, and that's important because ionizing radiation is essentially something with enough energy to knock electrons off of atoms, which is where you get these nice particles or clusters of charged particles. Now, the leading theory at the time said it came from rocks. So that makes sense. You know, you're at ground level, you detect it, it could be coming from something around you. But in 1909, a scientist named Theodore Wolff measured the rate of radiation at the top of the Eiffel Tower, which is about 300 meters. Now, the rate he detected was just under half the amount that they had predicted would be detected at that height, so something wasn't fitting with the current theory. Now, Victor, shown here on April 17th, 1912, more than 100 years ago now, wanted to really figure this whole thing out. He decided he was going to use a balloon for that process. So in 1911, his balloon went up to around 1,100 meters, or 7/10 of a mile. With better equipment than had been used before, it found essentially no change in that radiation reading from ground level up to where he was. But on April 17th, 1912, he made it up to 5,300 meters, or 3.3 miles, during a near total solar eclipse. Now, at the time, there were two theories on where these things could be coming from. One was rocks. Some people said maybe the sun, but the sun was not really the mainstay of that theory. It was typically rocks. But since it did not decrease with the sun, which was blocked by the moon at that point, it can't be the sun. He went up in altitude 3 miles, a little more than 3 miles. So, and he got no difference, so it can't be rocks. So he determined it has to be coming from space. And in fact, indeed, these high energy particles are coming from space. And cosmic rays turn out to be really useful in a lot of ways in science labs, and sometimes for various experiments. They're actually still used at places like CERN and others, even when you have equipment around to generate your own particle waves. Still using those cosmic background radiation signals turns out to be quite useful in a laboratory environment. And with that, he helped us learn even more about the world around us. So the other day, somebody asked me, why are all these fundamental science projects so important that they win a Nobel Prize? Well, we're going to get to that in a minute. But Carl Anderson won for the discovery of the positron, which would not have been possible without the work of a bunch of other Nobel laureates. Now, what the heck is a positron, right? We hear it on Star Trek, we hear it on different sci-fi shows, but what really is it? Well, first, let's look at a positron, which is an anti-electron. In fact, the photograph you see here was taken by Anderson while he was doing his work in 1932. And what you can see is that the deflection and direction of the particles in the ion trail coming off of the detection show it's behaving as if it is positively charged, but really it's exactly the same mass, it's exactly the same everything as an electron, except it's positive instead of negative. So you now have the first detection of antimatter. Antimatter of all varieties is the same size as the matter equivalent. And now this is where it gets really interesting. When the two collide, for instance, a positron and an electron, they are instantly annihilated and they release an amount of energy according to Einstein's famous equation, E equals mc squared. So you can see where antimatter gets its reputation in science fiction movies, because the moment it touches regular matter, which is all over the place, you get this really interesting release of energy. Antimatter does have other uses. It's actually currently used in some forms of radiation therapy and some industrial imaging, but this project by itself is actually one that I think displays that standing on the shoulders of giants saying as much as any other. So let's talk about that for just a second. Now, On the Shoulders of Giants is not just the name of a Stephen Hawking book, although it was. I truly believe that scientists do learn from the people that came before them in ways other than just, oh, that guy had a good idea. It was, hey, that guy made giant mistakes. I'm going to go figure out how not to make those same mistakes. So it is kind of, you learn from both the good and the bad work that was done. Now, this particular prize, I do believe that the detection of the positron was an event that took place only because of the giants that came before him. For instance, Dirac was the first theory of antimatter. Dirac won the Nobel Prize in 1933. Antimatter was detected using a cloud chamber. We talked about Wilson, who was the first one to use them in a lab. He won the Nobel in 1927. And then Anderson was actually using a cloud chamber to study cosmic rays when he discovered the positron. And again, he shared the prize in 1936 with our cosmic ray hero, Hess. So if it hadn't been for the two Nobel Prizes that came before him and the one that he was standing right next to, would we have actually known about antimatter, or would Professor Anderson have won his prize? I really do think that scientists need to learn from the history as well as the current state of things, because if you don't remember your history, you're bound to make some of the same mistakes. And especially with theories that didn't necessarily work out all that well, you might go down those same rabbit holes. So I hope everybody's enjoyed this one. I really do think this one is greatly connected to others. Please don't forget to click subscribe and like. And if you want that bell icon for warnings on when we drop new videos, that would be good too. So everybody have a great day wherever you are. And we will see you on the next video.